Can everybody hear me okay? Let's just pop some things in. Oh, great. All right, let's try to be in the general channel for now. Over as far as text goes, I'll try to pay attention to the general channel. And everyone should be seeing my screen. So 2, 4, 6, 8, 10, 11 people so far. We got a minute left, so that's not too bad. Let's hope things go relatively smoothly today. Knock on wood. Computer crashes and things. I've only had one student crash so far, and I haven't had any crashes so far. Tempting fate. How's everybody else's classes been doing with regards to technology and everything? Working out? Generally? Not too many reactions, okay. Anyone on campus? How does campus look? How's that fun and excitement been? Everybody's been getting their COVID tests and whatnot. I haven't been subjected to that just yet, but we'll save that for later, I guess. Okay, so I'll kind of start digging in here. So what I'm going to do today, I figured for starters, might not be a bad thing to look a little bit more at the actual sort of setup for your projects. Where are things? We still had a few issues with regards to kind of setting up OpenGL, setting up GLEW, Glue, and GLFW, and so on. At this point, it might not be a bad idea. You are offered the option. You can get just the straight up binary libraries for Glue. You can get them for GLFW as well. Soil is going to come in later, and most of the GLM math, the math libraries is also going to come in later. So really, as long as you get Glue and GLFW kind of squared away, hopefully before the weekend, so you can kind of try some of these things out, you should be able to run these programs. Those are going to be the main ones, and they are available as pre-built libraries. So rather than suffer through too many things, you might just want to grab those. Now, of course, in order to use them, you still have to have things kind of set up the right way. So we'll talk about that as well. And certainly, Visual Studio isn't necessarily the simplest piece of software ever made. So it's worth kind of discussing a little bit how to potentially set up Visual Studio. This is how I have it set up. There's not one particular way to do it. There's a million, trillion different ways. So let me talk about, I guess I have to reference kind of where certain things wound up on my machine. So that's kind of important. Let me go to my C drive over here, and I'll show you for a moment. Now, I've built a bunch of the libraries and things here in the root of my C drive, but that's not really the important part for now. The important part really is that I have this OpenGL template folder. Hopefully you can kind of see that. View, can I increase the view? Never really increased the view size in here. Can I Control plus? Nope, can't. All right, well, take my word for it. There's OpenGL template. That's the folder we're looking at here. And within there, there are some things. When I built Glue, I wound up with some information here as well. These aren't important. This part, the visual info text, exe, glueinfo.txt, glueinfo.exe. That just runs and let me know the latest versions. That's part of the installs of some of the other ones. But the really important parts are these directories up here, the lib directory, and you'll see in the lib directory is where I have my glue32.lib, my glue32s.lib, glfw3.lib, and so on. Now these are all built, these are the versions that are built for x64. So they are 64-bit libraries, okay? So if you see x86 versus x64, these days we're no longer, we hopefully, everybody should have a machine that's capable of running 64-bit, and if you're running Windows 10, you should really be running 64-bit Windows applications. So that's the first thing. x64 is your friend. You always want to have that. So when given the choice, use x64 libraries. So I've built these all specifically for x64, okay? So in here, like I said, there's the glue libraries, there's a GLFW library, there's also the soil libraries. Whether or not you have debug versions of these libraries isn't necessarily important because we're not going to be actually debugging these libraries per se. So it's okay. You don't need to necessarily have the debug versions of these libraries. Unless if you want to build it and you want to step into things, you can certainly do that, but that's not really important. What's most important is that you have the static versions. GLFW here is, I believe it's just the static version. Glue32s is the static version compared to the Glue32 lib, which is the static library that links to the DLL. But so it's the important ones. You'll see Glue32s, GLFW3, and soil. All right, and I'm going to be using soil S, which is also the static version of the soil library. So other important things in there are the include directory. So we have the GL, which is going to have some of our glue stuff in there. We're going to have glad. You will not have glad. Don't worry about glad. I have a couple of different environments on here, so you don't have to worry about glad. You will have a GLFW. You will have eventually a GLM if you don't already. GLM, we don't really build a library for at this point. So when you do use it, it kind of just sucks in the code it needs from there. And eventually you'll have a soil 2 as well. Okay, so soil, once again, is the simple OpenGL image library. Glue is our GL extension wrangler. GLFW is our sort of our glue for Windows, or a glue, basically a window handling routines that, OpenGL operating system handling routines. So things like popping open windows, doing basic I/O, and so on. Right? So that's what they're all there for. All right, so this is the directory that I'm going to refer to from the Visual Studio environment in order to get those libraries. I know when we were talking on Tuesday, I had mentioned using glue.dll. That was glue32.dll. That was actually an artifact of some things I was doing with regards to kind of hopping back and forth between glad and glue, and you shouldn't get into that. We should just use the static version of it. Life will be much easier. This way you don't have to worry about copying libraries around nearly as much. Okay, so we'll try to make sure you have static versions. And what static means is basically everything's going to be pulled into your application that you develop. Your exe file is going to have all the libraries it needs. It should stand alone from that perspective. You won't need external DLLs and so on. And so you don't have to worry about conflicts. We don't have to worry about random version issues and so on. All right. So that's in my OpenGL.template directory. Depending on how you've named things or gone through the install, you may have a different name. But I did set up a template for Visual Studio, so it will refer to everything in here. All right. So inside my Visual Studio project, and yours probably looks different than this, the typical ones. What I've done here is I've actually built this so that I can have multiple projects within the main project here. Okay, so it's not a requirement that you organize things this way. I just found it to be a little bit easier to deal with kind of everything in one place. So you'll see for now I have chapter 2 the background, chapter 2.2 point, chapter 2.3 error checking, chapter 2.4 files, and so on. And then each one of those are basically a solution within this solution. Solutions are kind of the environment, the space that Visual Studio likes things to be in. It wants them to be in a solution. So I have an overall solution called text programs. I created that. And then within there, you can right click and you'll see you can add, and you can add new solution folders. That's how I did that. You can add new projects. You can do all sorts of things, but I just created some folders in there. Doing that is something you can do, but not super critical. But in case we're looking at this, you should see that. Now, you may have something more that looks just like this, right? Chapter 2 something, or my first project. All right, so this is a solution here as well, okay? So maybe you don't have a solution within a solution, you just have a solution. All right, so within here, I have this solution, and I have one C++ source file in it, just my main, which is this one right here, or at least it's a reference to it. You may have that, depending on how you have things set up. Again, Visual Studio, you can get very, very fancy with regards to where your different program files or where your different source files live and so on. Most of the time, if you just kind of create a simple Visual Studio project, Visual Studio solution, it will handle kind of putting things in the right place. And you'll wind up that with your source code being probably in that same project or solution directory. It doesn't have to be there, but it by default will probably be there. All right, so here's main CPP, no big deal. Now, if I click on the solution and I right click, go down to properties, and here's where things get a little bit interesting. Here's where we're going to tell Visual Studio how to find the libraries that we're interested in. Also potentially define any C++ defines, so that ahead of time it can kind of define things in the code for us. So a preprocessor definition, there's only one that's going to be particularly important. So what most people first deal with is right here. This is one that people are having some issues with, the additional dependencies. So the linker, if you choose linker input, you're going to probably see additional dependencies. This is telling you what libraries are needed for this particular solution, this particular project within there. All right. Now you'll notice at the top, you shouldn't ignore this. It says configuration and platform. All right. You may see release Win32 or something like that. All right. So what we want to generally have is all configurations, all platforms here. Okay. I'm not sure why that is showing Win32 versus. Okay. All configurations, all platforms. We'll do that to make life kind of easy. And then within here, there's probably a bunch of this is already pre-populated for you, everything from kernel32.lib, user32, and so on. The important ones that we're going to be adding, of course, are glfw3.lib, glue32s.lib, and eventually soil-debug or soil-s, whichever one you want to use, and also OpenGL32.lib. Okay. So assuming you're on x64 Windows, this is kind of where things should be. All right. Now, also what we're going to do, you probably see, as long as you have a C++ file in there, main or something like that, you'll see that you do have a C++. Actually, let's go to this one first. Visual C++ directories. All right. Here, you may need to add, and I think the older versions had an additional include directories. If you're in Visual Studio 2017 or earlier, you might have an additional include directories. In Visual Studio 2019, you just have include directories, and you can see that I have added my include directory inside my OpenGL template directory. Okay, so it's going to go through its normal Visual Studio and Windows SDK include paths, and also include my OpenGL template include, which has all of the stuff for glue, GLFW, and so on. Okay, so that's that. Now, that should get you through the first couple of programs. Now, there comes a time, depending on how you are working on things, eventually as you start including shaders in your program, and we'll talk more about how shaders work in a little bit. Shaders are sort of an external resource that your program, shaders are basically programs that your GPU, your graphics hardware is going to be running separate. Normally the code we're building here, the executable we're building here, this stuff is all running on the CPU of your machine, right? So we're building it specifically for an x64 Windows platform and so on, right? But we don't necessarily know exactly what graphics hardware is, so ultimately, we are going to be compiling shaders on the fly. Okay, that's what's really happening inside of an modern OpenGL program, is that there will be a certain amount of compilation of your shaders. And because of that, we have to load those as separate programs, and we'll kind of get into that later. Depending on the reason I'm mentioning it now is depending on how you have things set up, your current directory or your working directory, which you'll see up here in debugging perhaps, this working directory, that may need to be set to your project directory or wherever it is that your shaders are, right? Because if you are using the debug, just launching it as a debug here, that is the program, or that's the directory that it's going to be looking for your shaders to be in. So that's something to be aware of later on. So just remember, there is a working directory. That means when you are debugging something, when you execute something as using the debug up here, that is the directory that your program is going to start off in. So if there's any important things for the program to have, whether they be shaders or opening up other files like textures or images, whatever, that's the directory it's going to be in. Okay, so that's another word of warning about Visual Studio. So important things. So be aware of the working directory. Your include directories. Your executables are going to wind up, depending on how things are built. For example, you're going to see this is, a lot of the time it's building things in different locations because you might have a x64/debug directory. So Windows is using the combination of this configuration and platform to kind of figure out where to put things a lot of the time, and potentially which libraries to link things to, right? So you, generally for now, probably want to keep things as similar as possible, and don't accidentally set something for x64 or 32. Like if I change this now and only added OpenGL template that include for Win32, well, then when I compile something for x64, it wouldn't be able to find that. That's why, especially in the case of something like include directories, it's important to make sure you're telling it that the include directories are all configurations, all platforms that you've added to that. Now, one other thing that is, because we're using glue and because we're doing it statically, once you have a C++ file, and I think this C/C++, this only starts to show up when you have at least one C/C++ file in your solution. You'll see it has this preprocessor definitions. Now on here, actually I have this set a little bit lower down. You can use this preprocessor definitions. Let's see, do I have it? Or maybe I have it all the way set all the way up here. No, where is it set? Oh, there we go. So it is set for x64. Actually, I could have set that for all of them. So my bad. So we want to have this glue_static set as a preprocessor definition. And that's because glue needs that to be set before any of the glue include files are included in your source code. If you don't have that, it's going to do some odd things and assume it's going to, want to include it does a few things with regards to kind of shaping or decorating the function call names, in addition to just saying, oh, okay, I'm using the static version or the static version of the library or the DLL version. It does some interesting things. So I set it here. You can also, if you wanted to, you can set it just at the top of your file, and you would just say define glue static. Whoops. You can do that. Okay. One way or another, just make sure that is defined. The reason to do it inside the other one is just in case you'll see in some of these there is going to be a couple of source files, like there's utils and main, and the more things you have in there that potentially are accessing glue, you just want to make sure that you've made that include for all of them, or made that define for all of them. So that's why I did that as a preprocessor directive set in the Visual Studio IDE environment. Okay, so any questions on that? Let's see here. Trying to check over in Discord. I haven't seen anyone type anything yet. But certainly, if you have any questions, now's a good time to ask. Did I leave anything out? Or have you seen any odd things that you don't think what I just said will help with? Yes, no? Okay. Well, let's move ahead then. Hopefully, oh, question. Sure, any questions? You can either type or you can turn your microphone on. Either way works, should work. Suspense is killing me. Yes, I can. That's okay. Mm-hmm. Mm-hmm. Okay. Well, what can happen if you like? I'll show you right here. So in my chapter 2, if I wanted to create another program in here, I can say add new project, and it's OpenGL Template, and I will say next, and I'm going to put this one, and this is a little bit weird in mine in that I'm putting the, well, I'm not put anything here. Chapter 2, non-existent, 12. And I'm actually putting all of my output in kind of a one common space, which is a little bit weird, so don't get too freaked out by this, that thing that I just did right there. But imagine I was adding a project here, or just opening one from the template, say chapter 2, 12, and you'll see it'll create that. And it does include the main that I happen to have in that original one here. Now, what I do is I just say, okay, I just remove and delete that original source. So then I just add the ones that I'm interested in. So is it that you had one in there that it's then maybe you've deleted it, but then the template builds it assuming that it's there? Is that possible? You never, if you deleted it from the template directory that it's then using to pull things back into, that might have been it. So at this point, one thing you can definitely do is you just want to always be in the habit of just deleting that. So if you see a reference under source, can you just delete that reference and it's okay? So you, yeah, I'm not sure then. Yeah, that's, Okay. All right, let's try to figure that one offline. It should be. I mean, normally you want to have. The odd thing is if you don't have any C++ files in there, the template, or at least I've, and I'm sure maybe there's some intricacies of Visual Studio to get this to work. But you'll see, like if I go to Properties now for that particular one, you'll see that C++ doesn't have any configuration, or C/C++. I can get to the VC++ directories, but I can't see any C++ options or configuration properties in there. So that's why that one winds up being included and I delete it. I believe that's why they took that approach, and that's kind of been consistent with my experience. But I'm not sure what happened or why it's trying to reference something that doesn't exist. That is odd. So we'll come back to that one. Okay. So now, at this point, and like I said, you're free to organize this however you like. I just found it, and you can, I'll just say, Google is your friend with regards to, setting up solutions within solutions in Visual Studio. Certainly, we could probably fill a whole semester of just, the intricacies and idiosyncrasies of Visual Studio, Visual Studio community, Visual Studio code, and so on. But this seems to work reasonably well for me. So now I have just a single C++ file in this first one, which is the chapter 2_1 background, so the normal file. Hopefully you have something that does look like this. Now, quick question. So I'm assuming everyone, if you get the text from the textbook, or excuse me, if you get the text from the bookstore, you get an actual physical copy of it. You will also get a CD which has a bunch of this text in it, has these actual programs set up in it. So I still hopefully, it is something to reference. It's great to go through and actually type it in yourself so you're kind of familiar with each line and so on. But if at the end of the day you are losing your mind and something's just not right, that is a place you can reference it, and so it's something to be aware of. So it's another good reason to buy the textbook. So this first program is main CPP, and you'll see, like I said, it's referencing glue up here, and it's referencing GLFW, and it happens to be referencing, including IOStream just in case we want to print out anything, just information on the screen. All right, so the first one is really, someone had asked today also, what happens when this runs? So let's go ahead and run this. So I'm going to choose that, and now I'm just going debug x64, and because I have it set up to just run selected, if I hit local Windows debugger, and unfortunately this does load on my my default laptop screen. So this is what I get. So this is my actual GFLW window. So this is my context for my OpenGL, and in the background I just have the equivalent of sort of a shell that is running the executable here. Right, so that's why we want it with two windows. We sort of have the shell executable and then the actual GLFW display or window context up here. Right, no triangles, nothing all that fancy going on in there, but I do get a red background in here. All right, so you'll see now I can go ahead and close that. So let's take a quick look at what's going on in here in case you're wondering. And you can, if you have built for debug, we can actually go and step through this code, of course. For those of you not familiar with the Visual Studio debugger, definitely want to get familiar with it. It's very useful. It's your friend. Okay, so now I've set some breakpoints here. I actually really even set the breakpoint at the very first line of code here, and just say local debugger, and you'll see it stops immediately, and I don't get a red window to pop up. I just get this black window here. And then I can start to step through my code. So step over each thing, and eventually, what just happened? And I can't drag it onto the screen, unfortunately. Trust me, there's a window that has been formed on the other display that unfortunately it just can't move because we're stopped in the program here. And if I continue on, a few steps in here. Maybe it'll allow me drag it in. No. Still no. There we go. Well, let me drag a little bit of it before it stopped again here. So we're kind of stepping one piece at a time through the program, through my buffer swapping and so on. So for now, I'll just say, go ahead, continue. And now it'll happily, everything will be normal. All right. So what's going on in here, and it's also, certainly the text, we'll go into this as well, but let's just look real quickly, because this is really the simplest, and maybe I'll bring this up here. I basically have sort of 3 different presentations I'm going to jump back and forth to a little bit here. So let's use this as a point to talk about, from the text. This particular presentation is a bit talking about the graphics pipeline from the perspective of the text. Okay, so accompanying the code that you're going to have inside of Gordon and Clevenger's computer graphics programming in OpenGL. This is explanation of that. Okay, so let's talk a little bit about ultimately what's going on. So they like to talk about this in terms of Java and OpenGL, but basically it's the same thing for us. In terms of C++ application and so on, we can talk about the same things kind of going on. So the end user ultimately sees the display monitor and is running an application with OpenGL calls. Okay, so the end user runs a program and sees the results on the monitor. So the end user thinks that they're just doing something from the CPU. The end user never talks to the GPU. They never really run a GPU program. They never do anything like that. But the programmer, on the other hand, we have developed the OpenGL program, and we have also developed this GLSL shader code. So we're actually going to be dealing with and writing 2 different programs sort of simultaneously that ultimately talk to one another, or maybe even really it becomes even more than 2, the more different shaders we involve. And ultimately, the graphics hardware these days, one of the nice things, I'm sure, hopefully this isn't the first time you've heard this, the really big advancement that's happened only relatively few years ago, within the last, decades, 15 years or so, is this advancement in GPU technology where there's basically massively parallel computing going on your graphics cards, right? In your graphics hardware. Your GPU architecture is just tons and tons and tons of little execution units that are running lots of code in parallel, which is very different than what's going on in the typical application on your computer, which is normally, maybe you have, you've spent the $3,000 on your CPU, and you got a Threadripper from AMD, and it's got 32, or I forget anyone know what's the maximum number of threads, or excuse me, of actual cores on a Threadripper GPU now? Is it 32 or 64? I think it's 32 cores. Somebody should just be like answering that right away, right? So you were posting stuff about the 3080, 3090 cards and so on. You don't, any AMD Threadripper fans out there? No? Nobody? All right. Anyway, so that's the big difference. We have this GPU code that's going on, and also CPU code that's going on. So all of our C++, 64 cores. Okay, so latest is even crazier. All the code that we are compiling, that we're really compiling inside of Visual Studio, is this bit here, the C++ application with our OpenGL calls running on the CPU. We're going to be writing these shaders, but they are not actually compiled inside of Visual Studio. They're compiled in the application, actually as it's running according to whatever GPU it actually is running on, and so on. So it's a very different model than a lot of people typically think of when they think about you write a program, you compile a program, and it runs on your CPU. And probably most of your courses and most of the programming you've done so far probably you haven't done shaders before, I'm assuming, or any kind of GPU, or what they call general purpose GPU, general purpose graphic processing unit coding. Okay, so this is why supercomputers tend to use these same architectures, and a lot of these architectures are actually based on the advancements that have happened in graphics cards as well. So that's why NVIDIA is such a big name in kind of massively parallel processing in terms of supercomputers and stuff as well. What's going on now? So that's a little bit of background on that. So we're going to kind of jump over to another presentation in just a minute to talk more about that. But for now, let's say that. Yep. Amazon Web Service supercomputers, 80% NVIDIA cards. Very true. Yeah. So things have come a long way. So normally here's the C++ application up here, right? We have some C++ application that then ultimately, I'm going to double check every so often to make sure I'm pointing at the right screen, staying on time. The C++ application is the one that starts off in charge. You know, it really kicks things off. It controls the flow of things generally, right? All of the stuff that's going on the GPU and the graphics card is really as services to your main program, right? So it's not like your GPU is going to say, okay, do everything and then just forget about it. You know, it's still going to be saying, okay, what's happening? You know, its code is going to be running at 60, 140, 120, 144, whatever frame rate you need, because it's going to be doing lots and lots of stuff in terms of, you know, shuffling things back and forth between main memory and the GPU and kind of coordinating things and saying, okay, well, this model should now be here, the camera should be there, but then ultimately letting the GPU do the kind of burdensome, make sure all the vertices get where they're supposed to be and they're transformed correctly and they're pixels on the screen and so on. But the C++ application really is the thing that kind of kicks things off. And then we have these shaders and processing units that are over on the graphics card that is going to run on their behalf, right? And some of them, I just think of these as, you know, sort of buzzwords for now. We have a bunch of different types of shaders. So shaders are programs, right? They're sort of, you know, specific and they're tailor-made for graphics processing, or they started off that way. But a lot of times you can actually, you know, do some much more generalized things with them. So, but for now, there are some very specific ones to in service of what we need for graphics. So, for example, we have vertex shaders, tessellation shaders, geometry shaders. We have the rasterization of the screen, which happens when we actually want to get pixels on the screen. And that happens through the use of fragment shaders and so on. And ultimately, there's also pixel operations that happen to remove hidden surfaces, do different things. So we have this, what is called a pipeline, right? Because there's not just one processor involved. We are passing things between lots of different processors and different tasks and going through different states during the course of the program, right? So that's why we refer to this as a pipeline, right? Information is flowing, data is flowing depending on what is necessary to be done with it, how it needs to be touched, how it needs to be manipulated, and it's moving from place to place to place, or like through this pipeline of different operations. Okay, so you'll hear that word a lot, the GPU pipeline, right? So this is our main simple OpenGL application. That's why I wanted to pull this particular thing up here. And this is, you know, basically, you'll see it awfully familiar. It's over here on the left-hand side. And this results in our red screen there, hopefully. All right. And this is sort of the most basic, a very basic OpenGL program. But the weird thing is, you'll notice, remember I did all that talking about shaders in the pipeline and all that sort of stuff, but we didn't do anything like that in the first program. So you may be asking yourself, you may be feeling disappointed if you've already done that. And you say, well, I didn't load anything into a GPU. I didn't compile any shaders or any code and so on. And everything still sort of worked, right? I didn't deal with any, and I didn't draw any triangles and all that kind of fancy stuff yet. Well, there are certain things that you can do without necessarily getting into the pipeline. And one of the interesting things that's really happening now, the version of OpenGL that you're using, that we're really focusing on, isn't the basic OpenGL anymore. Okay, we're far closer to, now this next big change is going to be with Vulkan and Metal and so on, the next big versions of OpenGL. Well, the not predecessors, the descendants of OpenGL. So we're starting off things you're going to get a lot of experience, and certainly the shader experience and so on is very important going forward. But historically we're at this very, very interesting point. So far in this in program 1, we haven't even written a shader, but we did go through. The important part to go through here is really just the setup, right? The setup for GLFW, the setup for glue, kind of some basic things, get a window on the screen, and then also tell it, okay, if no input or nothing happens causing the window to close, just keep running. Okay, so this is really just a very, very simple shell of a program. So let's look at what's going on, and you can, there's all these things that are happening within a specific order. If you want to read documentation for every one of these things, there are literally, of course, thousands of different API calls for OpenGL and Glue and GLFW and all those things on top of one another. There's lots of good resources out there. There's some I want to point out to you. OpenGL has, of course, its very own wiki. The Kronos group, KHRONOS.org. They're the folks sort of behind, or they're the keepers of the standards these days. They're also the keepers behind the standard for the newer Vulkan as well. So this is a great site for information about OpenGL in general, and also kind of new stuff that's going forward. We're going to look back and forth as well on that quite a bit. So you can always refer to the OpenGL wiki at the Kronos.org. There's also another site that I just found out fairly recently about myself called docs.gl, which will let you look up any OpenGL API call, and you'll see it has, for the different versions, we're almost exclusively going to be using OpenGL 4X, the most modern version of OpenGL, and talk in a minute a little bit more about what that means. Right? OpenGL has been around for a while. The initial versions, 1.0 back in the day, we've come a long way between there. So now we're GLL 4. So when you see that, that's the version we're on. So docs.gl, also a great place for information. So for example, I could just, one of the oldest calls in the book, GL begin. Whoops. GL, and it's good. It found, GL begin. You can see, okay, this one goes back quite a ways, So anything you might encounter in any of the programs, great place. Just type in the function name, and it'll help you find. So GL attached shader, perhaps that's a good one, and it'll give you, exactly what's going on and related things, other related functions, which versions of OpenGL it's valid in, the error return codes, and so on. So this is a great resource. Be aware of that. We'll post that somewhere. Okay. So those are two great sources. I think I also mentioned Cherno's OpenGL. If you want, he does a good, if you want to spend an hour in the stuff that we just covered in half an hour, or another bunch, that he's great. I consider him a textbook. Really nice guy. Worked at EA for quite a while on some of their engines. Really phenomenal stuff. Has some great stuff in game engine architectures as well. He worked in one of the game engine groups at EA. It kind of comes from that perspective. So hours and hours and hours, hundreds of hours of video on there if you want to take the time to watch all of his things. I'll try to give you some hints about the particularly important ones. So, all right. So this is the basics. So we are, you can look these up on any of those resources in addition to in the textbook. So what's going on, basically, it divides itself into three parts. The first part, what we're doing is we're setting up GLFW. That's the part we have to get an OpenGL context. We have to open up a window. We have to have something that we're going to be kind of rendering into, working with, where all our stuff is going to be going on. So the GLFW library is used as a way of abstracting out the operating system GARF, the things like, how do you open a window? That's different on Windows versus Linux versus Mac. How do you get at the mouse? That's different on Windows versus whatever. So we need a standard way of kind of dealing with those in terms of the OpenGL context, and also knowing how does that operating system effectively get at the drivers for, some of these things as well. So that's why we have GLFW first, right? That's at that level. Now, then, once we get that basic bit behind us, then we start to deal with more kind of the specifics of working with stuff in OpenGL. So GLFW on its own really doesn't do a heck of a lot. It really just kind of sets that environment for the sort of operating system stuff around that and gives us that context. That's important to have that context because we can't use glue, we can't really use the OpenGL stuff without that context, okay? So we set up GLFW first. We have this GLFW init function, right? That's the one that says, okay, set it up. Can we do the basics, right? It checks to see if we got a valid return, basically if it returned true, which means that it was okay. If it's true, then we can continue on, right? And we can do things like, set up some window hints that we want to say, all right, we want to be using at least this version, at least these functionalities for OpenGL in here. So this, for example, is saying, okay, we're going to be using version 4.3, so all the features of that. So we can forget about, older things and so on. And then we actually set up a window, right? This is the size of the window, and we can give a name to the window, and we have some additional decorations and things we don't have to worry about just yet, all right? But this will give us a GLFW window that then we can use to create the real context that we can kind of set things up so OpenGL can run, all right? So here we are. That's the first chunk of code. One of the most important parts, of course, is this GLFW make context current, right? Because glue cannot run without a OpenGL context, okay? That's, again, this is that window that we opened. Ultimately, that is the OpenGL context that we're working with. That's why all the graphics show up inside that window, right? So once we have that, then we can initialize glue. And we start to see immediately, you can recognize that whoever wrote glue is a different person or group of people than the people that wrote GLFW. How do I know that? Well, they decided to do things, they decided to do things slightly differently, and everyone who develops a library has choices to make. So you'll see they decided, okay, in order to see whether or not they succeeded, they say, okay, we succeed if we return glue underscore okay. They don't just return true or false like the folks who developed GLFW decided to do. So it's slightly different. We have different methods here, but ultimately, you're going to someday be writing libraries and codes. Well, you're already writing your programs, and you're deciding how error handling is done, how error codes, success and failure, and so on. So these are design decisions that sometimes are made arbitrarily, and so on. Okay. So then we set up, the swap interval. We're going to do some things with just basically what's going to happen in here. We have some double buffering. I'll talk a little bit about that a little bit more in a bit. We initialize the window. So we sort of set things up. And then ultimately this loop here, this is your main, could be your game loop, your main program loop. This is the thing that's going to happen over and over and over again until somebody tells that window to close. Right, so we have GLFW window should close, and that's going to be the action of someone stopping the debugger or clicking the close box. There's no key equivalence up there. You can't hit escape, and I don't think you can hit escape and have that quit. But the act of closing that window is basically saying, okay, pop out of this loop. That's what's going on there. Otherwise, it's calling these things over and over and over again. So the first thing we have in here is this display. Now, display, again, in this case, it's sort of the simplest possible OpenGL program you have, in which all it does is it clears the context. It clears the window that it's in, okay? And we're clearing it to a color. So you'll see 1.0, 0, 0, 1.0, right? The last one is the alpha channel, which is we have color is not just red, green, blue. We also have transparency. Okay, we'll talk a bit about that more as we go into things. But this is why it's a red window, because we set red to 1. All right. OpenGL likes things to be normalized between 0 and 1. So 1 means full red. And other things, other programs you may have seen, like 0 to 255 for 8 bits, or 10 bits is 0 to 1020, something like that. OpenGL likes working in floating point normalized terms, right? Likes floats. Once upon a time, You know, we liked using integers and bytes and those sort of things. These days, floating point is fine. Floating point is accurate. Floating point is fast, right? You've probably never had to deal with, you know, optimizing for non-floating point architectures, and you're lucky. So that's why our color space, you know, basically everything is between 0 and 1. For 1 is full red, okay? And we're just saying, okay, clear the context according to the buffer, to color. All right, that's all that's happening in this one, right? We're not using anything with the time. We're leaving that for later. And then ultimately we say, okay, swap the buffers. We have frame buffers and so on that govern, you know, what is actually shown to the user. And then we check for events. And this is really something that's just being done to see, okay, is it time? Is there anything going on with the operating system? Anything going on with, you know, user input and so on? So that's just basically drawing that red, or telling OpenGL to draw that red window over and over and over again as quickly as possible here, just running infinitely forever inside that loop. When it does break out, then we do some cleanup. We destroy the window that it created. We terminate GLFW, and we exit, and cleans up around it. Okay. So that's the basics, the very most basics of there. And it didn't use any shaders. Okay. This is the one thing where there's no vertices that were actually processed. There was no geometry, there was no context, there was nothing that was actually processed. So that's why we can get away with no shaders on here, because there's really no information being drawn other than clearing a buffer, right? So it's literally sort of an empty screen from that perspective, right? So that's why this is the simplest kind of thing we can go on. So let's diverge from that for a moment. How does that sound? All right. About the buffers thing. What does it mean to swap buffers? Yes, I'm gonna talk about that now. And hopefully go into that right now, if I can find the right window. Not that one. Where is my... Here we go. Now, you'll have to excuse me, but you'll see it says game architecture on it. And yes, I'm in the process of changing the game architecture, and this class now are becoming their very sibling classes now. So we talk a little bit about the general architecture and graphics in terms of this. So we're going to use stuff that would have been in game architecture, but now we're covering it a little early. Not going to necessarily go into all this, and certainly you're not going to get the homework that's assigned from this one, so don't worry. So let's go back. I'm going to jump over some of these things. Now, so we're going to talk a little about history first off. Now, the interesting about this history is this is the history of 3D and GPU technologies and kind of 3D graphics within this architecture. All right. So it's not a history of computer graphics in general. And actually, maybe it's a good time to say, well, before that, I'm going to go into something really, really fast. And this is just going to be a whirlwind tour of a history of computer graphics in general. All right. So hopefully your seats are buckled. So we'll go this a little bit for starters and get this kind of out of the way. We'll do this real quick. Just 10 quick slides. History. Brief history of significant developments in the field of computer graphics. Now, first off, computer graphics officially showed up in around 1960, but the first graphic systems were in the mid-50s. The Air Force, of course, before games, everything came out of the military and NASA. Now everything comes out of games, right, in terms of development, which is kind of fun. It's kind of we're paying back for that, you know, whatever. So a lot of the initial stuff that came out of things, the early computer graphics, you know, just started as soon as there were computers. We needed some way to interact with computers, so graphics kind of happened, right? Initially, I was supposed to ask a great question here. So what was the first main breakthrough in computer graphics, right? So don't worry, I'll come back to buffers. We'll get to buffers. We have to just go back before we can go forward, right? So my question to all of you, what is the most, well, except I've already given the answer away. The first big advancement in computer graphics had nothing to do with pictures, had nothing to do with mice, had nothing to do with things. Yes, it is, but we'll get to there. Don't worry. We have to understand how to get, we're going way back in history, and then we're going to move up to buffers. You know, buffers in general is a much, much more general concept. So we shouldn't just be saying buffers. We should be referring to frame buffers. And sometimes, there's lots and lots of different types of buffers. So we have to sort of step back before we can go forward. All right. So one step at a time. So the first big advancement in computer graphics was text. Now, I'm sure you're not thinking that text was, it doesn't feel like a big graphics. You don't think of text as being graphics, but it is absolutely graphics. Okay. In the early days, the Manchester Mark I, Turing's first computer, all those machines, you literally, and up until even, I think, with the Altair systems and so on, you literally were you were programming and looking at things. You were looking at lights that indicated ones and zeros that were all numbers. Right? There was no interface between you and the computer other than numbers. Right? Text, if you think about it, hieroglyphics and alphabets and so on, they are graphics. They are the kind of these symbols that represent something else. They're a graphical symbol that let you get at some meaning. There's some underlying piece. So text certainly is graphics. To go from 0 to 255 to say, okay, 40 means a blank space, or off the top of my head, I'm forgetting what my ASCII codes are. But ultimately saying, okay, this number is this symbol on the screen in this font and so on. That's a graphics question. That's, so the first big thing that had to happen largely was text, showing text on screen, because early displays, let me make sure you're seeing this, hopefully. Yes. Early displays were none other than, let's see, I'm going to do this. See if this will... that's silly. There we go. How's that? So early displays were nothing but numbers. So we've come a long way to actually have things. But now in the 60s, things kind of rapidly advanced, right? Way back in the 60s, we started having applications such as Sketchpad at Sutherland and Evans and Sutherland, and all these places. Largely they were flight simulators and military type systems. This was the dawn of interactive computer graphics, right? People would display something, radar plots, or engineering things on a screen to basically say, okay, we need to interact with that, we need to manipulate that, we need to do CAD. CAD was also an early thing, computer-aided design and computer-aided manufacturing later, right? So a lot of these concepts appeared pretty early on. We had things like pop-up menus, constraint-based drawing, hierarchical modeling. So things were happening very, very early on as a result of the interaction between the user and the computer, right? So they were still real time. They were about that communication back and forth. They weren't necessarily about pretty pictures, but they were about that real-time interaction between users and computers. So fairly early on, in the 70s, IBM came along, and the Palo Alto Research Center, this is a great moment in history, Xerox, Palo Alto Research Center, pioneered a whole bunch of techniques like the mouse, graphical user interfaces, drop-down menus that aren't that far from what we use today. It's funny, Windows 1.0 actually looked a lot more primitive than the stuff that was shown at the Park in 1975. So it's kind of interesting that ultimately, let's see, Apple followed Park, and then Microsoft followed Apple, and then back and forth and back and forth. So everybody was sort of inheriting these technologies from one another, and that's ultimately where kind of things came from. But trust me, we're almost there. Okay, a lot of these early things that sort of became interesting at the time then was coming out of this notion of kind of pixels on a screen, right? So paint systems started to happen now, right? So you had this buffer. Oh, I used the word buffer. You had this frame buffer, this pixel buffer, this array that ultimately we were putting things into, symbols like, here's the shape of the letter T, which is made up of pixels, right? So we would push the pixels that were associated with the letter T, push that on the screen, and then the letter I or the letter X or the letter whatever. You'd actually be setting those pixels on the screen, right? And that led to these sort of, once we could manipulate text, get the text on there, then people started to say, okay, what can I do beyond that? Shapes and forms and so on, right? So this is some of the earliest things. And in parallel, we also had image processing as sort of a different field where we were digitally altering images that ultimately we were saying, okay, now analog television was happening simultaneously with kind of computer graphics and so on. So we were taking signals and digitizing them, manipulating them back and forth, right? So things were happening fairly quickly in the 60s and 70s. And eventually, the 70s and 80s, we started getting these notions of, okay, how can we jump beyond that? How can we go beyond pixels, right? So it was largely, everything was pixels up until that point. But eventually, we started moving towards what we now use a lot, which are triangles and meshes, all right? So I'm sure now these things may look, sort of familiar to anyone who's done kind of low-res graphics, or you've done low-poly modeling and low-poly gaming and things. And if you've played games within the last, certain amount of time, you've probably seen polygons, and they're not a new thing. They've actually been around for quite a while. Okay, so we're going to jump back out there for, I think that's enough of that particular history, and we'll go back to, we'll go back to this history over here, right? So there's a lot going on. You can see it kind of stopped over here. Late 70s displays, August 1985, array technology formed, later became ATI, right? So this kind of takes us, that was meant to really kind of take us up to, the ancient history of computer graphics, right? Why things kind of came about. It's mostly around, that kind of interfaces and so on, then TV and entertainment and so on. So in the 90s is kind of really when 3D graphics and the commoditization of computer graphics sort of happened, right? Before then, we still had video games. We had things like Nintendo and all those Super NES systems and all that, and they were based largely on drawing pixels on the screen, right? You would draw an image of something by taking a block of pixels and pushing that somewhere, right? So these were in buffers. We might have something called a sprite buffer, which might be a picture of a tank or Sonic the Hedgehog or whatever, and we'd take that, blast that bunch of pixels as an array or a buffer and push that to somewhere on the screen, or convince some hardware to kind of move that around for us. So it's largely based on that sort of manipulation of things, right? So this is what was going on. We had the late 70s, we had controllers, early games like the Atari 2600 and so on. We had ATI come along in 1985. OpenGL goes all the way back to 1992, right? So people started thinking, yep, there's going to be some interesting things going on. NVIDIA releases the NV1 in 1995. DirectX comes out in 1995. Now, right about this time as well, you'll notice we didn't mention the Sega Saturn, the PlayStation 1, and the Nintendo 64, right? 3 platforms that made a big break from all the other traditional graphics systems. Now, prior to that, there were some things that started exploring 3D computer graphics as well, but they were largely 2D systems, right? They were largely pixel-based systems. You had a buffer on the screen. You had a pixel for every buffer, a pixel for every spot on the screen. I think, let's see, let's jump through this history quick, right? So we have 3DFX, we have NVIDIA coming along, 2000 hits. We start to really have the commoditization. 2001, NVIDIA, ATI, and Intel, they have now graphics card businesses are coming out of that, right? The GeForce 3 is the first programmable Vertex Shader. So now the new era of even 3D computer graphics kicked in 2001. 2002, DirectX 9 and its high-level shading language. Now we have brand new version of OpenGL, which had its own graphic GL shader language, had it happen. And now today, now even this is out of whack. Of course, now we're up to not the 3080, but we are up to the 3090. Oh, why can't I? Whoops. Let me edit that. Oh, I'm in the PDF version. Sorry. So we should have, we're even beyond this. Wait a year or two, everything will change. So we have these new modern APIs, DirectX 12, Vulkan, Metal, and so on, right? We have virtual worlds. We have all sorts of things going on. So that's the history. Now, let me take a sip of a beverage. So much has happened in order to get pixels on the screen. Ultimately, that's what it's all about. On your computer, if you're looking at a display, which you probably are, there are pixels on the screen. You're probably familiar with that term. And each pixel has a color on it, right? Some combination generally of red, green, and blue. Okay. So every location on the screen, and probably, I guess the vast majority of monitors these days are probably 1920 by 1080, which is an HD resolution. So you have 1920 pixels across the screen. So a row of pixels is 1920 pixels. And you have 1080 of those rows. So you have basically 1920 columns and 1080 rows of pixels. So about ballpark, about 2 megapixels, 2 million pixels on your screen. And that's your frame buffer. What the frame buffer is a certain amount of memory, usually in your graphics card. Nowadays, it's in your graphics card. And that's what holds all those pixels. Any spot on your screen, there's ultimately 3 values in some way, shape, or form that your graphics card tells your display to show. And that will determine what's on the screen. So that's the final solution. The thing that the graphics card tells your display. It says, okay, here's all the pixels, and you probably actually have a frame buffer in your display. Sometimes you may have noticed, sometimes you can even crash your computer, and in certain circumstances, a display will hold actually hold the image and so on. But the display will have, an array that basically two-dimensional array that is in charge of holding all of those pixels on the screen. So at each location, you have a red, a green, and a blue value, and that's what makes up the frame buffer. Okay, a buffer can contain anything, but this is the case we're specifically talking about a frame buffer. Okay, so what's going on normally is why we have this thing called swapping of buffers is that in order to be efficient, we don't want to be necessarily creating. Imagine writing a book, right? Sorry, change direction here. I faked you out there. If you were writing a book, you wouldn't want people to start reading the book until you were done writing the book. Stands to reason, right? Because you don't know how it's going to turn out, and who knows, maybe you might just decide it's no good and you're going to start over again. And ultimately, imagine you have only one piece of paper that you can write on, and after you write that piece of paper, you turn it in, and someone's going to read that, and so on. So normally, you want to be showing somebody the book that is the last one you read and working on your next book, right? Or at least you give someone a page to read while you are writing the next page, and so on. So imagine that page sort of being the buffer. And at some point, if you only have 2 pieces of paper, you'd be writing one page of your story on a piece of paper, then you hand it to someone to read, and then you start writing your next page. When you're done with that, you hand that to them to read, and they hand you back the other page, and you somehow erase it real quick, and you start writing on that page again. And then when you're done, you give that to them to read, and they give you back the other page, and you erase that, and you start to write again. So those pages are the buffers for your story, for your information, for whatever it is you're communicating with your user there. And the act of exchanging those two is that buffer swap. Okay, that enables us to do a lot of things. There's a lot of efficiencies in that. Ultimately, there's a lot of you can be doing things a lot more smoothly on the displays, and you don't have screen tearing and other weird issues that we can talk about as a aside some other time. But let's see. I will check my time. Did my clock stop? All right, we're moving quite a ways along here. All right, so we're going to take up a good chunk of time. We're not doing individual meetings this week, which is why I'm going to be talking probably more than we normally do. So that's the concept of the frame buffer, right? Does that kind of, or we came a long way by virtue of the dawn of graphics, which is the reason for this is really up until these new GPUs came along, the main thing we did, the main way we programmed is directly manipulating these kind of large buffers of pixels. And sometimes it was writing directly to the screen, right, which is why things look so crude and why things displayed and updated so slowly. It's largely because we were working directly with this frame buffer. And what a graphics card was really nothing more than, a lot of the time, one of these graphics buffers. One of these, maybe 1-2 frame buffers. And you wrote directly into that, this Visa buffer. And that's all there was to it. And ultimately, with a frame buffer, you could display anything. If you implemented everything as software, and there are ray tracing programs, and if you use Blender or you use Maya or use any of those type of things, sometimes some operations are still done on that level. They're not handed over to a GPU to do something. You are directly manipulating, right? If you're editing an image in Photoshop that's not made of triangles, you're still manipulating frame buffers. So for our purposes in this class, we're largely going to talk about 3D. We're largely talking about kind of what's the commonality of game programming, game engines, and kind of where the industry is right now. So we're mostly going to be talking in terms of 3D, but we'll jump back and forth and revisit 2D a little bit. Any questions? All right. So here's our frame buffer. If it's blue, there it is. We have a set of values at every location on the screen that's exactly the same. There's our frame buffer. Images are nothing more than arrays of numbers. They're buffers. They're frame buffers. Their appearance depends solely on how you interpret the data. If you say it's a red, green, and blue value, okay, that's what you pass to your display. That's what you have. That's your buffer. Right? We have this, we're back to this point. Our paint, it showed how some of the earliest programs that we had were these paint programs because we were directly manipulating the screen. And that's really what we're doing. We're painting on the screen, right? Pre-GPU, here's where we were. We had CPU, it wrote to the frame buffer, and ultimately that frame buffer got written to the display. Now, things have changed. Got a lot trickier. Pixels don't just go to the frame buffer and to the screen, right? In your first OpenGL program there, you really didn't do much more than that. We really just said, okay, here's the red color. It's just going to be put on the screen. So we really didn't do anything with it, which is why we didn't see any shaders. We didn't take advantage of the pipeline. All we did was empty the buffer. We just cleared it, the frame buffer. So to really do anything in OpenGL, we're going to have to, and certainly modern OpenGL and forward, we really have to be programming shaders. That's taking advantage of our graphics hardware, right? Early on, we had these fixed function pipelines, right? Certain things that the GPU card was responsible for, right? And in here, you'll see, for example, the fixed function pipeline where there's like certain things are going to be handled by certain hardware, basically certain functions. It's not programmable, fixed function versus programmable. So the CPU would do, set up the geometry for the scene, figure out where the models were and all that kind of stuff, set it up, and then hand it off to fixed functional hardware that would then do certain things, like maybe transform the model, or might move it around, or might move a camera, or it might change the lighting. They were very powerful, but they were fixed. They had to do these certain things because they were assuming that certain techniques had to be performed on a 3D model in order to do graphics, right? It assumed, yes, you must have a transformation engine, you must have a camera that does certain things, you must have some sort of basic lighting, and perhaps the lighting is only flat shading or garage shading or simple interpolated shading, things like that, but it had fixed functionality. Right? So there's certain things it could do. And ultimately, you see these last couple of steps here, this rasterization. Did anyone actually watch the history of computer games? This is going to be one of the questions. Where does the term rasterization, where does the word rasterization, or raster, where does that come from? What does it mean? Look it up. Watch that other stuff. I might ask that during one of our talks. Be prepared. Right? Now, textures and fragment shading. Okay. Show of hands, who's heard of textures? You, I'm sure you've heard of textures. I'm going to have some kind of... Okay, good. Show of hands. Everyone react. That's what we should do. The first person can raise their hand and everyone react to that. Okay. Textures. What are textures? Textures look an awful lot like an image. They look an awful lot like a buffer. In a lot of cases, they look an awful lot like that RGB value at every location within there, right? It might be a picture of the side of a building or the image that's on the side of a Minecraft block. That's a texture. Ultimately, it's an image. It's red, green, blue, maybe alpha values, right? So typical textures, I should say, not all textures, but they are also buffers. They are arrays. They are that. They may not be RGB values, but textures are typically arrays like that. They are some sort of raster-based, sort of array-based data structure that is used in that similar way to represent kind of a buffer of things. All right, so we're going to be coming back there. This notion of frame buffers. You'll see some similarities, right? So the fixed function pipeline in OpenGL, similar. We mentioned this thing called immediate mode. And in immediate mode, which is historical, we never want to do immediate mode, where we had specific things that we could do. We would specify each individual vertex and its attributes with individual API calls. We would say, okay, here's a vertex, here's a vertex, here's a, or maybe here's a triangle, or here's a rectangle. And we say, here's a vertex. You know, we've dealt with everything, like spit out a vertex, and then it would deal with that, right? It would immediately deal with that vertex, you know, putting things together. And then you had, after that, you had some kind of API call to transform things. A lot of these will be buzzwords for now. Right? This is background, so hopefully as you start dealing with things, I don't expect you to know what an identity transformation is yet, or any of these transformation functions, rotation functions. We'll get into that next week. We're going to talk a lot more about math as well. These things will make sense. We had ways of drawing triangles, right? Here was our drawing where we said, okay, I'm going to begin to specify a group of triangles according to vertices, right? I'm not drawing pixels anymore. That's the important part, right? We're not touching memory locations on the screen. We're actually describing geometry, right? So we open up a context to say, okay, begin. I'm going to give you vertices for triangles, actual geometry. The first vertex is at this location, 0, 1, 0. The next vertex of that triangle, right? In order to draw a triangle, I need 3 vertices, 3 vertices, right? They have to be. That's what a triangle is. You got that? Hopefully you know that. If you don't, we should talk. Anyway, so you'll notice the big new thing is, of course, now we're working with geometry, not with pixels. Ultimately, we're going to need to get pixels on the screen, though. So after we specify those triangles, we also have to specify a color, perhaps, for the triangle, right? Because we have geometry, and geometry isn't enough alone, right? Geometry has to have color to be shown on the screen. You say, okay, here's this location, but what's at that location? It needs to have a color. And then ultimately, how does that color get in the right location on the screen? Or where is it pulled from? Or where is it, you know, how do we correlate that off-screen versus on-screen? And that's something called texturing. You know, how do we relate these textures and colors to the vertices, to the triangles, to what we have, right? So even the fixed function pipeline is basically this dance between vertices, vertex shaders, and fragment shaders, the 2 types of shaders, where we say, okay, here's how we deal with geometry, and here's how we create pixels based on that geometry. Here's how we fill in. So you can imagine one draws an outline, sort of, or draws a geometry. The second one decides, okay, how do we color that? How do we shade that? How do we, you know, put pixels on that, right? So the fixed function pipeline is pretty straightforward. You know, you had one set of inputs, one set of outputs. Everything was sort of understood to do its thing. Now, the modern version, and this is where we're at, so just to let you know, things that we're going to be going across here. Now we have lots of programmable bits. More and more in our GPUs, we can do more. And there's even more now beyond this in the version that we're going to talk about. Potentially, there's now the new, with the 3080 cards, well, the 2080, or the 20 series, the RTX cards from NVIDIA, for example. Now we have ray tracing units on there and some programmable things we can do in that. So this is always kind of changing and advancing, right? But the typical programmable pipeline now, we can specify vertices, you kind of create our geometry on the central processing unit, our main core, and then we can program how these vertices, how these meshes, how these geometries are kind of manipulated by the graphics cards. And then there might be certain things that they do have in common, you know. That's what's happening here, vertex processing. And then ultimately we have this programmable fragment shader, so we can do all sorts of fancy things like fog and transparency, or a higher level transparency, and particles and bump mapping and height mapping, all sorts of different things where we are really taking what we're sending, these buffers that we're sending to the graphics cards, manipulate it before it winds up on the screen. Right? So this is a much more sophisticated, much more programmable pipeline. Okay. So I'm going to leave off some of this stuff for now. We'll get into there. But ultimately, just to jump off a little bit of things, it's about the triangles. Right? We're going to be dealing with triangles ultimately. So the next, hopefully one of the first things that happens after you do your program here, and let's see, did that? Okay, let's stop that one running. It's still running in the background. We wound up with, you know, just a background on that first program. The second program, if you haven't run it yet, it decides, the purpose of the second one is to show you, okay, can I draw a point on the screen? Right? In order to draw a point on the screen, you need to specify a vertex that it's going to draw on the screen. Right? So even before there are triangles, there are points. Right? We can draw a point on the screen. You can have a vertex, a single vertex. Right? Now, vertex is not just a location on the screen either. Right? A vertex is going to have something like a location and a color, right? Or location, a color, a normal, which is a piece of geometry we'll talk about a little bit later. It might have a bump map. It might have all sorts of interesting things in terms of, you know, specular highlighting, you know, all kinds of different lighting that it can do and so on. Some very fancy things, ultimately. But the basic unit is, of course, the vertex, and from the vertex we then make triangles, and then from triangles we make meshes, and meshes are models, and so on and so on. So we can kind of get there. So we had our first program that drew our blank background. The second one draws a point on our screen. Okay. Now, in order to draw that point, we are in here using shaders. All right. Now, thankfully, if you've run this already, there's not a separate shader program, not a separate file at least, but it's actually, there are two little programs that run that are embedded within here. So if you have any questions, stop me at any point. I am recording this, so hopefully this is still recording. Yes, it is recording. So this next program, it does a bit of shading because it can't just be a point on the screen. It has to be a point that ultimately something happens to it. Okay. So in our program, if we look down here at the main part, you see a lot of common things. GLFW and Init sets up the windows, the hint, so on, context, swap interval, everything all pretty much the same. Init, slightly different now. Okay, we have this init. Now, this is something we'll start to get into much more, certainly as we get past, you know, the first program. You take some of this for granted for now. We'll get much more detailed in terms of, you know, what vertex arrays are, what vertex buffers are, what vertex objects are, a lot more. But suffice to say, we'll just talk about the general need for them. Okay. So before you can draw any vertices can get drawn on the screen or processed, you have to set up shaders. We have to sort of, now we're compiling the program for the CPU. We need to put the programs that's necessary over on the GPU. Right? Certain earlier versions had kind of fixed functions, and you might have something by default, but for our purposes, let's assume we have to program the GPU to do something. Okay, so we have this function here called create shader program. Okay, so that's going to create our shader programs to run on the GPU. Right. So here, GLU int. So this is a OpenGL unsigned integer. OpenGL loves its unsigned integers. Everything is dealt with in terms of these indexes or indices, or it has integer references to things. That's going to be one of our best friends in terms of referring to an object. When we ask something, we set something up, we often get these indices back, which are just integers. Okay, so a lot of time you'll see these GLU ints all over the place. So here's our two programs. Here's our two shaders. Here's our first shader. This is our Vertex Shader. And this is our Fragment Shader. They don't look like much, and they, in fact, are not much. They're pretty brain dead. The first bit, you'll notice it has a little main in here. So it's got just one little function that it's going to call. We're going to set up this one little function that all it does for a vertex, right? So this is a string. Now I'm assuming you're all pretty good with C++, right? So a const char star here, this is basically a set of character strings here, basically. Not real strings, but character arrays. So there's 1, 2, 3 lines. They're terminated with a new line at the end, the first two. So we specify in this little shader source code, there is a version number. We just basically tell an OpenGL, yep, this is the version that we're expecting you to be. That's the first bit of heads up. And then here's our program. We're just saying, okay, here's our main program inside that shader. And all it does is it returns a value, right? GL position is sort of a magic, it's definitely a magic name here, right? It's one of the things that the shader knows about. Right? The shaders have their own language. There's GLSL, GL, GSL. I was freak out in the middle of things. They have their own language, right? In OpenGL, it has its own language. Shaders are the shading language. And even Microsoft DirectX, it's a little bit different. There's HLSL, anyway, I'm just forgetting the acronyms here. So they have their own context. It's going to look a lot like C, C++, but it's not exactly like C and C++. So here's, again, it looks an awful lot like a C program here. And for our purposes is right now. But there are certain keywords and variables that it automatically knows about. One of them being GL position. So when this shader runs, the purpose of this shader, it's a vertex shader, and it's meant to work on a vertex. Normally it would hand it a vertex and it would perform sort of some operation on that and then hand you back a manipulated version or some information about that vertex for it to use and kind of pass it on to the next stage in the pipeline. Okay, so it's this first step in the pipeline is to say, okay, what is the real position of this thing? As far as the screen goes, we have some geometry and some point. What's the real position of that point? So run some process on there. This program is really, really simple, and all it does is just say, okay, the first point is at 0. That's what this vector 4 is, a position. 0, 0, 0, and don't worry about the 1. W. Don't worry about that. Okay. So our first shader, our vertex shader, is doing nothing more than setting a position to 0. Saying, okay, the result of the running of that shader is 0. That's going to get run once. Why? Because of the way things are set up down here. You might notice GL draw arrays 0, 1. Right? So there's only one thing that's going to happen. Right? So that's going to happen once. And then to color that shader, right, we have two parts. We have, okay, manipulate the geometry or the vertex of that shader, the the position of that vertex using the vertex shader. And then the other shader, its job is to figure out what color to do, to color to make it. And you'll see here, again, we have the version 4.3. And this, in this one, the fancy bit of predefined thing we have is this out vec4 color. So that's telling us, okay, the output of this shader is a color. Okay, so when it says, okay, what do I put at this location? It's already figured out the location based on, you know, some manipulations that's going on with the vertex shader. This one is saying, all right, here's what the color should be. And this is a brain dead shader. All it knows how to do is pass back RGB, the color blue. So it says, okay, anything that wound up being specified by this program is going to be colored blue. Okay, so we basically are saying at position 0, draw blue. That's all there is to it. The other thing, now this, what happens next is basically the process of compiling and linking your shader, right? So these are the parts where we're now, like I mentioned before, we are compiling the shader for the particular platform we're on, and we're pushing that over to the actual GPU hardware on the fly, when the program actually runs, because we don't know exactly what graphics hardware we're on. So this is the part where our program gets to customize itself, gets to kind of target itself to that platform, all right? So we create a vertex shader officially here. We get an index back to it. We officially create a fragment shader. We create the programs that are, we create a program that combines those two, right? A program is a combination of shaders. We tell our library about the source code. Now we're giving it the addresses of these two shaders. We compile them. Then we attach those shaders to that program. We link it, and we're all set to go, right? So just like we set up everything in Visual Studio out there, this is the bits we're doing in here, right? We have the corollary inside the program where we really got to do all that. How am I doing on time? Okay, my watch is correct. That's where my watch stopped. Okay, so this create shader program is the setup piece of things that gets done for the OpenGL shaders, you know, the stuff that we couldn't do in Visual Studio. Right. So that gets set up. Now our shaders are good to go. Our GPU has some code that's ready to work with. It has a program. We've sort of programmed the GPU. The next step is to give the GPU some data to work with. Now these shaders are I can't overemphasize how brain dead these two shaders are, because they can do exactly the same thing. They might as well be fixed function. They don't take anything in, right? They are stupid shaders. They're just brain dead shaders. However, in order for them to run, you still need to set up your vertex arrays. You need to tell it, okay, there's some number, right? Because if you don't tell it, yeah, there's some vertexes to work on, it's not even going to run the shaders, because it's going to say, well, a shader needs to run on a vertex, right? There has to be a vertex to process in order to do anything. So I have to tell it, yes, there needs to be some context, there needs to be some data. And that's what's happening next. We're setting that up. Okay. We'll get into the specifics of kind of what's going on in this. It'll make more sense as we have more complex programs. But for now, you just need to know that you need to set up a vertex array. A VAO is your vertex array object. Okay. For now, we just have a single one. And then we're going to bind the vertex array, which means basically this is the context for the program that we're going to be using. Okay. OpenGL and your graphics hardware is kind of a state machine. You'll hear that used a lot, that term used a lot. It's basically you're kind of setting up everything and then executing it, right? You set up all this state, and then you say, okay, run, basically. So the array object is going to be, ultimately you set it up, and then you bind it to that's saying, okay, now that's the state potentially to run, right? So that's the important thing. We have our setup here. We set up our renderers. Whoops, I just modified some code. We set up our shaders. We set up the data that those shaders think they're going to use. They're not really doing much of it. But now we should be kind of good to go. So we initialize things. We come down here. We finally get to display. And to display things, all we have to do is we tell it, first off, we tell it to go ahead and use that program that we set up. Use that context. Use those shaders. And then what do we want to do with it? Now we have to tell it about the arrays, about how to process things. Now we are going to set up a little bit more state, and this is unusual. A lot of time you don't use single points. You will be using more triangles as opposed to points. But for now, we're using a single point, so we do have this ability to set up some state, which is GL point size. That's going to say how large is a point. So if you draw a point, this point on the screen, even though it's a single vertex, it actually is a 30 by 30 block of pixels ultimately on the screen. That's going to happen here, this point size. Right? So we say, okay, a point is this big. So no matter how many of them you have and so on, if you have 10 of them, each one of them is that big. Right? And we tell it, all right, now it's time to draw. Use everything that you have set up. There is one vertex to be processed, and it's just a point. There's only one point to be processed. Go ahead and do it. I'm exhausted. I run the program. Hopefully, there. I press that, and I wind up with that. Ta-da. A lot of work to get that point. That's one point on the screen. It's blue. It's at the center, you'll notice. Should be at 0, 0. So the center of my context is at 0, 0. If I wanted to change that to be red, I would go up to here to my brain dead fragment shader and red, green, blue. So we'll say 1 and set that to 0. So now I'm saying, okay, shader, okay, fragment shader. Now, it's red. The good news is here, you may run into this later. The nice thing, because this shader code is directly inside here, I didn't have to worry about where it's located. I didn't have to read the shader. More sophisticated, basically any shaders that get a little bit beyond where we are right now, we're going to want to load them from other files. Our source code is going to be a lot more complex. We don't want it to be sitting inside of here. And you may even want it to be something that is dynamically something you can change, right? So we're going to be a lot more sophisticated. Now, say I could even do this. Say I wanted this to be 0.5. Move it around. Whoops. I'm going to move it much more than that. Oh, no, that was the color. All right, well, let me show you what happened there. I turned it into kind of a salmon color there, which isn't what I intended to do, but that's what I did. Let's say I did this and run it. Now, it's, again, it's just, it only knows one location, so it moved it there. Z didn't mean much to this. Okay. All right. One of the next things that you're going to do, I'm not going to go into it, I'm going to let you check it out in the book, is loading shaders from files. Right? And this is much more a programming exercise than an OpenGL sort of thing. What you're going to wind up doing is you're going to read a file that contains your shaders. And the code up here is basically how to read a file from disk, from some location. You get a file path, and it's going to load that. Vert shader, frag shader. You notice they have this suffix GLSL. It can have any suffix if you want. You're really the one reading them in and doing stuff with them. But that's going to change. And then we start to see, okay, specifically, we've moved these shaders out into their own bits there. Okay. So hopefully that makes sense now. And then around 5, we start to draw triangles. And notice the fragment shader on 5 isn't much of anything. The vertex shader, however, is a bit more sophisticated. It's still probably the most brain-dead vertex triangle shader you could imagine, because even program 5 is really, really dumb with regards to what it's doing with its vertex array objects and things. It's not really smart about much programming in here. I'll leave that for some questions and stuff in maybe in the Discord chat, since we're at basically 2 o'clock. How are we doing? Does this give you hopefully enough background now so you've had a little bit of a hint in terms of where we're going, how these things fit together, this notion of a pipeline, this notion of vertex and fragment shaders. The nice thing about the text is now, even though I've kind of blitzed you with a bunch of information, as you go through in the text, you're going to get these, a bit of a review on each of these concepts, and we're going to get through there. So the first set of programs here, all the way up to 2.6, they're not super complicated. The trickiest thing you may run into is making sure that the place you're loading your shaders from is your working directory. I assume some people have weird issues, and we'll just kind of help you get through there with those. But the programs themselves are going to look very, very, very similar, clearing the buffers and so on. The animation one, we use the word animation loosely here because it's really just bouncing a triangle left and right. So it's translating a triangle, sort of, in the most brain-dead sort of way. But it'll give you some experience with that. Any questions? Is everyone still paying attention? 2, 4, 6. Everyone's still tuned in, which is good. I thank you for that. Okay. Is that a question? Or is that a... So hands up is sort of a question. Oh, still paying attention. That's good. All right. Yeah. I think between what I've said here and the book, so you've gotten a reasonable amount of background from there. There's lots of other historical information out there. And we'll come back and keep kind of touching back and forth. What should we go up to in the book for the next class? Okay. You should have completed everything in Chapter 2. Okay. We're going to start talking about math next class. Okay. So basically, once you can do the exercises, the first couple of exercises, they're all going to come really quick, right? You're going to, solving the issues of getting everything compiled and linked is the big bottleneck for the first ones. Once that happens, then the only other bottleneck is probably, yes, slides will all be posted. Yes. And I do want to give, just in all fairness, and I do want to reference this, that I've taken things from lots of different sources here. One being, stuff that does come with the textbook. So the Gordon and Clevenger textbook is really great in terms of coming with great ancillary materials. There is also some great information in the history of graphics from UCSD and so on. So just a full disclaimer. I can't take full credit for all of these wonderful images and history and things, but there's lots of different sources out there. And some of it's covered in the book, and if you are following along in the Guha book, some of it is in there. It's just a wonderful bunch of things. So. All right. If there are no further questions, I'm going to stop the stream there. The stream will be available. I'll figure out exactly where it will be available. That will be the challenge. I'm going to try to get it up on LMS or possibly post it to my YouTube channel with a unlisted link that I will then also post on LMS and on the Discord. So I'm assuming that everyone can get at YouTube. I know there's some issues if folks are not in the US. Getting YouTube can be a problem, but let me know. Otherwise, I'm assuming YouTube can sort of be a common, lowest common denominator. So yeah, you should work your way up through the, get all the way done through the second chapter, start looking at a little bit of the math. We'll be getting into that. Okie doke. Great. Thanks, everybody. Have a good weekend. As best you can. Stay safe. Be well. Don't, remember, stay safe and be well. Let's not cause the semester to be any crazier than it already is. We keep hearing all sorts of terrible things happening on other campuses. Well, like I said, the class recordings, if I can't get them up on LMS or media site, I will put them on YouTube and post a link here as well. So there'll be, see you Friday. Wait, Friday? Is there no class next week? Tuesday's a Monday schedule. I was gonna wonder. I was gonna ask about that. Okay, no class Tuesday because of Labor Day. Well, in that case, make sure you've done. you should be done. You should be all set with chapter 2, and we'll just dive right into the math on Wednesday. Excuse me, on Thursday, Friday, in next class. See you next Friday. All right, we're off to it. And it's a smooth start. The faster you guys get into things, the faster we can get into like really fun advanced things. All right, have a great weekend.